Hello everyone. So there was this problem in my physics book, and I did it, and I think the answer, or what happens at the end, is kind of cool. I don't know why. It's weird. It's about Gauss's law. It says a charge Q is distributed uniformly over a volume of a sphere of radius r, capital R. What is the electric field at the center of the sphere? What is the electric field the strongest? And what is the magnitude of the strongest electric field? So I'm gonna do it because I want to make this kind of a mathy channel. Not gonna lie. So okay. So we have a sphere. I'm just going to draw a circle because that's good. It's easier to draw a circle than it is to draw a sphere. It has radius big R. And what we need to do is use Gauss's law to find the electric field inside and outside of the sphere. So it's uniformly the charge is uniformly distributed, so you could use rho as the charge per volume. So the units of rho would be coulombs per meter cubed. And so what we do now is we write Gauss's law. Gauss's law, if you want to be like freaking super technical, it's the surface integral of E dot dA. But for this, all we need to know is the flux equals the electric field times the area of the Gaussian surface that we're going to use. And so, since this is a sphere, you're going to use a spherical Gaussian surface. And I'm going to go ahead and erase this because it's in the way. I'll write it up here. That's a P, but whatever. Coulombs per meter cubed. Okay. So, Gauss's law says this is equal for a closed surface is equal to the charge inside the closed surface divided by epsilon 0. And so what we got to do is figure out the E field from this by using algebra. And it's pretty easy. You just divide by the area. Epsilon 0 divided by area of the Gaussian surface. That's confused me when I first learned about this. I didn't know what these stood for, but once you know what they stand for, it's pretty simple. So next, what we're going to do is figure out what Q is for the inside. First, we're going to focus on the inside of the sphere. So if we draw a Gaussian surface inside the sphere, it's going to have a radius of little r. And if we want to find the charge contained inside of that Gaussian surface, we would do the charge per volume times the volume inside the Gaussian surface. Not the volume of the entire sphere, but the volume inside the Gaussian surface. And to do this, we have to find both rho and V. So to find rho, we just have to look at the units. The units for rho are charge per meter cubed, as I wrote here, kind of not very neatly. So we just take the charge, Q, of this entire thing and divide it by the volume of that entire thing. And the volume, since it's a sphere, is 4/3 pi big R cubed. And this is the volume of the actual charge sphere, not the Gaussian surface. And the volume N is the volume of the Gaussian surface. So the volume of the Gaussian surface be 4/3 pi little r cubed. And then if we plug those back into this equation right here, we can solve for a usable value of q, which would be q over 4/3 pi big R cubed. This is qn, not. The q's are different. This is the q inside the Gaussian surface, and this is the total q of the entire charge sphere times 4/3 pi little r cubed. Looking at this screen is making me realize I need to have better handwriting if I want to do this. But you can kind of see. So we found q, and we can cancel some things. And I'm going to draw that over here. So q, make it look a little more nice. This 4/3 cancel. This pi cancels. And then we're left with qn equals total q over big R cubed times little r cubed, which is a very important thing, because this is what we're going to use up here in our Gauss's law equation, which is the key to this entire thing. So, actually, this equation, sorry, I'm talking about all of it. This one's solved. This is the one we're using, not this one. So now, you do E, sorry I'm off the screen, E equals Qn, which we found was Q over big R cubed, little r cubed, divided by epsilon 0 times the area, well, I guess times 1 over the area of the Gaussian surface, and the area of the Gaussian surface is just 4 pi times little r squared. 4 pi times little r squared. And that is the answer for, not the question the question asks, but that is the E field for this charge sphere. And so the question asks, what is the electric field at the center of the sphere? So where little r equals 0, because big R is a constant, so we don't even worry about that. So where little r equals 0. So when little r, which is at the top, is right here, is 0, the E field equals 0, because anything times 0 is 0. So the answer to the first question is 0. I'll write that here. 0 newtons per coulomb. That's the unit of electric potential. And so next we're trying to find the electric field outside of the sphere, and I'm going to erase some things so we have more room. But I'm keeping this solution we have over here. Okay. So to find Q, we'll define the electric field outside of the charge sphere. This is the charge sphere. Redrawing it just for neatness. It's a sphere, but I'm drawing it as a circle. This is going to be the surface. It's just a sphere that's concentric with the charge sphere, and it has radius little r again. And we're going to use the same law. E times A equals, what does it equal? That's right, Qn divided by epsilon 0. That's just N, as in like inside. So, what do we do first? Well, there's multiple things we could do first. We could find the area of the Gaussian surface. We could find the Q inside, which is actually really easy. So I think we're going to go ahead and do that first, because the Q inside is rho times the volume of the charge sphere, because all of it's inside the Gaussian surface. So rho times 4/3 pi big R cubed. And we don't have to solve for rho this time, because if we solve for rho, remember, it was Q over the volume of the sphere, so we're just going to get Q. It's going to just say Q equals Q, which, wow, you know, that's so helpful. We're going to divide by the area of the Gaussian surface in Gauss's law. Q n over epsilon 0 times the area. And area of the Gaussian surface is 4 pi times little r cubed. Squared. My apologies, not cubed. 4 pi times little r squared. Okay. Now, what do? Well, we just plug in Q in, which is rho times 4/3 pi big R cubed over epsilon 0. 4 pi little r squared. We can cancel the 4s, cancel the pi's. And we're left with rho times r cubed over 3 epsilon 0 r squared. This is the electric field outside of the sphere, so let's write that over here. Electric field outside of the sphere is equal to rho r big R cubed over 3 epsilon 0 r squared, little r squared. These are our two equations that we will use to solve the next two parts of the problem, which are the interesting parts. So the next part says, where is the electric field the strongest? Now, to use this answer this question, I'm going to draw a little graph to help you visualize it. On this axis, we have little r, which is how far you are from the center of the charge sphere. And on this axis, we have the magnitude of the electric field. Now, if we start from the inside, because we have to start from the inside. I mean, unless we start from over here. But who wants to start from over here? We're starting from 0. We're starting from r equals 0. At r equals 0, you can see that it makes the entire thing 0. And then another thing you can see is that I didn't simplify this all the way, because there's an little r squared down here and then an r cubed up here. So let's simplify that, and then you can see some striking thing. It's just r. It means it's linear. The E field is linearly proportional to r. All these right here are constants, so it's just the coefficient. So up until r equals big R, little r equals big R, we have a linear proportionality between the E field and the radius. But what happens after that? Well, let's take a look-see right here. Outside of the sphere, little r is in the bottom of the fraction, which means it's an inverse, but it's the inverse square relationship. So what's going to happen is right after, you're going to go down. You're not going to go back up like I kind of drew it. You're just going to keep going down. Which means, where is the electric field the strongest? When little r equals big R. So the answer is number 2. When little r equals big R, and number 2, the question was, where is the magnetic field the strongest? Now the question is, what is the magnitude of that? And this is what really blew me away. Because I was thinking, which equation do you use for the boundary of the charge sphere, where the electric field is the strongest? Do you have to use this one or this one? I remember in my book 1 was less than or equal to and 1 was greater than, so I figured you'd only have to use one of them, but both of them work. And here's how. So first, what we're going to do is plug little r equals big R into both equations. So then En, we have an r here, a little r, that's going to be a big R, and we have a big R here, which can be simplified to Q over R, big R squared over epsilon 0 4 pi, which I can do the big R down here. In E out, there's a little r squared down here, we can plug in big R for that, and it cancels with the big R up here. E out equals rho times big R cubed over 3 epsilon 0 little r squared. I'm so dumb. Little r squared becomes big R squared, which cancels with the big R cubed, and this just becomes a 1 big R. And you'll be looking at me like, these aren't the same equation. En is Q over big R squared at epsilon 0 times 4 pi. And the bottom one is rho times big R over 3 epsilon 0, which are not equal, but they are equal. Because remember, if we look back up here, remember that rho equals coulombs per meter cubed, which means Q equals what? Rho times the volume inside. This is Q inside. Equals rho times the volume inside, which is this volume, which is 4/3 pi big R cubed. Now if we solve for rho, Q in, which is for E out, just all the Q, is equal to 3/4 pi R cubed, big R cubed, equals rho. And we can plug that into this row, and where E, so that now we have 3/4 Q over pi R cubed times R over 3 epsilon 0. This 3 and this 3 cancel. This R cancels with this, and this becomes R cubed. And then we bring it back over here, and we have Q over 4 pi R squared times epsilon 0. What is that? Q over 4 pi R squared epsilon 0. Look at this. Q over 4 pi R squared epsilon 0. They both work. It's crazy. I mean, I don't see why they wouldn't both work, but the fact that they both work is insane. And you might be asking yourself, well, this is Q in, so isn't that going to be less than the total Q? Well, remember, we're doing it where little r equals big R. So Q in, when little r equals big R, is just all the Q. So I hope you've enjoyed my sloppy handwriting and my little physics thing. Yeah, I'm probably going to do more math videos that you are badly explained in the future. So stick around.